Welcome everyone to some more modern compiler and low-level talk here live on our channel. Another thing that I'm not particularly impressed with are sort of compiler optimizations, and you would think that after 50 years that the C library is already old. Apparently here 1972, 51 years, first appeared C language. That compile optimizations would be more amazing. Of course, they are more amazing. We came a long way in 50 years. Even in the 90s, compiler optimizations were not yet that amazing. That certainly also hindered Intel Itanium i64 with those bundles of instructions, with each instruction being a bundle of 3, and compilers for the longest time had the hardest time to parallelize code. So what are we talking? We're talking about compiler, the code for those who are new to the stuff and not that deep into those. Having C code is C++, but it doesn't even matter too much. Whether it's C, C++, C#, Rust, Swift, Go, and so on. So what a compiler does, but then I want to also move on. So compiler needs to tokenize all the stuff, right? What are parts of the programming languages? What are types? What are variable names, and so on, all the structure, and generate some internal representation, usually some kind of tree structure, SSA single, like nowadays often single static assignment form, SSA I believe, or other such tree forms, to then generate code. And then of course it's relatively complex, but to oversimplify this, then from some tree structure being, this is a for loop with this begin or with this loop control structure, with this body, and also of course with C++ all the template stuff, right? This is C++, this is even a template type name T. So for that, the compiler for C++, for generic code, the compiler even needs to instantiate that code multiple times for each type it is used somewhere, and then of course some templates having multiple types, so instantiated multiple times for this set of types. In the cheapest form, you could think of a glorified preprocessor of simply instantiating. Of course, in practice it is more complex, but like basically taking this text and like generating it multiple times, you could think of the easiest form of creating this set of code for multiple types. So all of this, of course, relatively complex, and theoretically compilers have like GCC and Clang, LVM Clang, and others. Previously, they also have been Microsoft and Intel compiler, but they are not competitive anymore. So basically, they all switched to LVM. Like AMD's also open, whatever. Like nobody cares. Basically, everyone is using, like everyone sane is using GCC and Clang anyway. So of course, optimizations are relatively complex. So what the compiler then does is generate machine code, right? There is an intermediate step, so the compiler would like then generate like this here from like this push and remove and stuff. But so this is a assembled binary form with what you see as a binary representation of the Intel variable length overly complex instruction set. The compiler would generate this text. Here, even earlier form where some like labels would still be in and other stuff. And so this is so there is an intermediate representation, but this is then the final binary that I disassembled here for you to. So this is, for example, it can also actually be linear. This is a matching C++ generated code for assembly code for this input. And so as you see nowadays, and also other complications, of course, since single instruction multiple data, when that was new, Intel MMX, AMD 3D Now, Spark, Visual Instruction Set, PowerPC Ultivec, and all the other forms variations, and nowadays SSE, AVX, AVX2, AVX 512, and variants thereof. And as you see, this state-of-the-art GCC or Clang compiler, of course, is using single instruction multiple data for loading more data in wider registers. So how is this relevant? So of course the compiler came a long way. So like when 3D now and MMX was new, you had to manually do that, right? Like if you were working, if you were John Carmack, you were working on your state-of-the-art 3D engine, you would recognize mathematic patterns and map those manually and write assembly code, right? In your, either in a complete new file or here inline assembler. I can show you how this looks. I usually don't write this. So either with files like this one, as you see, that is quite close to this disassembled code, just that here you still have alignment instructions and other things. So what does not impress me very much, in general, the compiler is of course generating quite okay code, but what is crazy is that what I really don't find impressive, and in my opinion shows that compiler technology came a long way, but someone says there's always the last 10%, right? So 90% is already amazing, but the last 10%, and this triggers me a little bit, and I also would think like other compiler engineers and operating system kernel and C library engineers should think about this a little bit more. Not really sure what's going on here in this chat stuff, which I don't see any. Strange stuff. Because it's some stuff. Not sure, this never happened before. So in this day and age, the Linux kernel, here in particular, but also the C library, is still manually optimizing as simple stuff as string copy, right? And so this is what I find so frustrating, and where I would say there is, in my opinion, still so much room for improvements. Whatever is going on in the chat. So that in the Linux kernel for RISC-V, for example, and that is the crazy thing, right? For each architecture, x86 already for decades, but even for x86, when there is a new AVX2, AVX 512, the Linux kernel engineers need to think and guru meditate whether they want to write manually hand optimized assembly code like they did here for RISC-V, right? So here's new for RISC-V. Support the new XBB bit manipulation extension, using it as a variant of optimized string functions, right? And so this is crazy stuff. And in my opinion, compilers should, because this code is super simple, right? I compiled you here the LVM C library function. So here's inline, so they have a little bit different approach here, apparently at times, like memcopy aligned access 32-bit. This is like what usually C code in glibc and Linux kernel does not look. But in the simplest form, maybe I should have actually loaded that. I probably should have a very simple form around here somewhere. One moment. Do I have either here? No, then, but here in... Here I have some poor man's implementation. So what we're talking about the simplest code, right? String copy. And so in the simplest form, I have here some simple form for some years for some reason. And I've 10, 13 years ago, leave in the comments below if this is the most amazing or not, whatever. So basically, for some, so you have string copy, and this is the whole family, right? It's not only string copy, it's also mem copy, string encopy, mem encopy? No, not m. Also other functions, right? String toc, string char, string whatever, right? There's a whole family of, maybe I have a couple of, so compare string, so string char, compare copy, no, maybe not, string lang, of course, string end string toc, string. And you might wonder, so why do we need to optimize this in assembler? Right? There is a gazillion trickery you can apply there for this. So normally it is just for all bytes and copy it, right? Let me even guru meditate so shortly. So initialize so normally I would, why do I even write it like this? Not, or maybe I would write because I need I here probably. So for some size t, I equals 0, and then as long as this string 2 to be copied is not 0, copy that string 1 to string 2. Usually this stuff is at times much less readable. Where did I park that here somewhere? Okay, we'll talk about this in a second. So this is the most simple code, right? And I would argue that this compiler technology that otherwise generates and vectorizes, right? To use single instruction multiple data, this is super complex, right? The compiler needs to analyze all kinds of 3D access patterns, like you have vectors, like X, Y, Z. The compiler actually needs to map, like be intelligent enough, not only recognize common patterns of vector math, of having multiple, like more than one dimension and using this in one vector, like, and even intelligent to map this. Often you only have RGB and or X, Y, Z, and then still mapping that to single instruction multiple data that usually has not 3 but 4. How do you call this? Yeah, parts, slices in these registers. And super complex stuff, right? And in my opinion, there should be nothing like compilers. In my opinion, compilers should know all the trickery, like all the alignment. And of course, compilers can generate quite some good code for that. That, in my opinion, there is no excuse that compilers for having sufficiently simple to understand. And I would even argue that, I said this before, I wonder that we do not have more functional programming, like more mathematical expressions of functional programming, of not this implicit form of dear little compiler and microprocessor for each step, take this byte, move it there, but to express like, I want this chunk of memory copied there. And sure, it is that, but this is very implicit and not very functional. Of course, there are functional programming languages. There are obviously over 100 programming languages, if not 1,000. But so, my point is, nobody should, like in the operating system kernel, and then, because it's also error prone, right? People send this in, like, hey, here's some bit manipulation extension optimized string routines with some surrounding code. Of course, you still would potentially need the surrounding code. But then also, like, clobbers, and that is the thing, right? Not only is, so what is the problem with this? It is super expensive to write. People need to guru meditate hours over their manually written assembly, which otherwise is a job of the compiler. And then it's even wrong, right? People send it in for review, and like I usually on YouTube, like yesterday with the P3, of course, make mistakes, right? Mistakes were made. And like clobbers, T0 clobbers means this code touches or modifies other registers, right? Like T temporary registers in the RISC MIPS, and like basically any application binary interface. Temporary registers, especially in RISC, where you have many of those, not like x86, where you have nearly no registers. And it's like, yeah, spoiler alert, T5 isn't used. It's like, yeah, so much too. That is why you don't manually write code. The problems of, I mean, obviously writing this code is highly time consuming, right? You need to really guru meditate and shuffle like memory, alignment. You need to take care of all the alignments, right? Like you basically need to understand your microprocessor inside out, and all the timing variants, all the unaligned excess penalties, like here, like, so what does alignment mean? For those who are new to this stuff, like, you do not, like, if you write code like this, you do not expect the compiler to necessarily generate it like this. And this is also not the fastest form, right? Because this is at 8-bit at the time, and 8-bit computers are already over since the 80s, right? We have had some 16-bit microprocessors, 32-bit, in the meantime 64-bit, and some even already 128-bit, like RISC-V already supports 128-bit. So that means the most efficient way to copy a string on a 386 is, of course, loading 32-bit at a time. Loading 4 byte, a quad word, or what Intel calls it, at a time, right? So that is like 4 times faster, easily, instead of 8-bit at a time. But you would not write this normally like this, right? Because in your programming languages where strings are 8-bit characters, you would write it like this. Of course, you can, so that means alignment. Alignment means your string is aligned, which often it is. And so you need to write, like, if you want to write the most high performance code, means you first align it, so meaning dividing it by 4, and the residuals, like first doing 8-bit copies, also for RISC, like basically for most, all of those optimizations usually look more or less the same, of course with assembly specifics here, aligning stuff, hard to read because and also use as mem move. Also, this glibc code, of course, overcomplicating this stuff with use as mem copy, instantiating this twice, like generic programming with meta programming with C macro preprocessor. When the difference between mem copy is that by the standard should not overlap. Also, people like Linus Torvalds even argue this is stupid. Always do mem copy. This is way too error prone. Nobody sane person, quoting Roberto Iser from Lua fame. You don't want undefined behavior in your programming language, right? Or you, like he thinks it's not a good programming language. Like it's not a good programming language when A equals B plus C is basically undefined, because in C or C++ or most other programming languages, this stuff can run concurrent, and basically you can't be sure what is in B and C because the shared memory can be at any time clobbered by other threads. But we digress. So in a high-performance implementation, you would align this to 32 64-bit quantities and then copy the beginning slow until it's aligned, like basically have a check, like some compare, ending that with this kind of pattern, 64-bit, 32-bit, then copying all the other stuff in those native quantities aligned, and then there might be some left over. Of course, all the stuff, especially with the string copy, it is very tricky because you basically need to check that none of those bytes inside the word aligned pointer quantity does not have a 0. There is quite some trickery to do that, because obviously you don't want to check every byte. This is why this complex this assembler manual optimized string functions are rather convoluted with all the trickery here. And then of course comes SIMD, right? With that it is even more complex, because for that you basically want to align that to 64-bit, 128-bit, 512-bit, and so on at a time, to very high performance load. And the craziest thing is ARM, like x86, even has some wrap move, repeat move. You can do a string copy in x86 assembly in like 3 or so instructions, just that they were not high performant. And only the irony is Intel, after 30 years, or like 40 years counting from the first 8086, actually added microcode implementations for recognizing this wrap moves to basically 40 years later, since some years now. Only recently this smallest 3 or so instruction string copy can actually now be fast, like nearly as fast as hand optimized SIMD for doing all the alignment and then using the largest loads the platform can do. And so the irony is that now, after 40 years, the hand optimized code might not necessarily be needed, or is not necessarily be faster, because now x86, but also ARM, has even some string optimization instructions now, believe it or not, also 40 years later. And so the irony is, for the latest processors, they even mark this in CPU-ID for wrap move is fast or so, invariant thereof, might be 2 or 3 bits for that. And my point is so I basically explained all the implementation difficulties surrounding this. And interestingly, the LLVM people, the LVM libc people, took another different approach. So basically they also have, like recently, as in 2023, May 10th here, libc at optimized memcopy for RISC-V. But the point is the same, right? Even although this, I think I didn't see any assembly in here, But they basically do this in higher level code, which I certainly applaud. So they have here if RISC-V and 32, then okay, I've defined some targets, thank you very much. What else? So here mem, so there is some new memcopy implementation header for memory utils. And so I applaud them to having a more high level approach of doing this once in like C++. Is it C++ or is it glorified C? But maybe, no, it has a namespace, so it's C++. So yeah, 2023, the LVM people at least write memcopy in high performance memcopy in C++. 2023, the future is now. My point still being, so I would find this, so I mean, we could, the problem is we compare apples and oranges. Memcopy, Google, ABC, whatever. Yeah. I didn't study this enough to recognize what is here now faster versus glibc, and it's not as good as glibc for now, so there's room for improvements. Pumping 16 bytes at once given the doubled numbers, large copies. So yeah, whatever, I would need this always at times a little bit convoluted here, before, after, yeah, whatever. Yeah, but here before, after, so that probably BM memcopy. So that is probably iterations per second. Always need to be careful. So maybe like 4 times faster here and 3 times or so faster there. Do they have here some? It's currently enabled for RISC-V 64 and RISC-V 32. Could be used for ARM32. Benchmark functions filtered 1.4 gigahertz. After not as good. Nah, I wish they would. But anyway, you need to study the details for finding out how much faster. Whatever. As you see here, this more high-level approach might not always be as fast as hand-optimized glibc, but maybe it comes close or whatever. But as you see, it could potentially be more easily reused for ARM32 and so on, given it is more high-level. So basically doing in high-level and having the LVM compiler figure out all the details. But I would even still argue the compiler, even this should not really be necessary. I would argue in 2023, after 50 years or so, or maybe in total of all of computer engineering, more than 50 years, but 50 years of C, of compiler innovation, I would argue the compiler should fully autonomously generate the most high-performance code by itself. I would argue, and so, I mean, we're not even talking vectorization. I mean, okay, we are basically, with SIMD we're talking vectorization, but the compiler can do vectorization, right? LVM as well as GCC. Yes, it is, I mean, the crazy stuff is, this, in my opinion, this should be the simplest test code, like the most naive implementation, I would argue should be the simplest test code of compiler vectorization. And so the only, I'm fully aware of all the complexities, and there are some. So for example, one thing is, how should the compiler know that this is I mean, theoretically the compiler can know that it is an exported function and not like, because obviously you don't want each small string copy where you just copy some 4 bytes of some network packet or some memory mapped IO hardware register and stuff. You don't want each copy of just some handful of bytes be expanding to some monstrous implementation of memcopy, which the compiler does already, right? The compiler already recognizes memory string patterns and maps those to, and optimizes those away, right, to build in memcopy. And whether that then is inline because it's small, or whether it's using a library function call, then depends on optimization size versus speed and so on. But I would argue it should entirely not be necessary neither to write this assembly code nor this higher level C++ code here of aligning stuff, right? So bytes, test align, distance to line, up to align, like, yeah, and then doing the rest, and load 64 aligned and stuff. It's crazy that we spend time. I mean, I appreciate the readability of that much more than writing. I was paid for 15 years ago, Blackfin DSP, like, sure, you can earn money with manually writing assembly code, also like at times maybe the best money, like obviously more than writing JavaScript for websites. Some voice over IP companies like, hey, we need assembly optimized high performance DSP code for our voice over IP telephony stack, right? Or ITVEC image processing and stuff, right? I in my career was actually paid good hours decades ago for hand optimizing stuff to ITVEC, to x86, to SIMD, AVX. Although it's getting rarer, and it's also not something I regularly would want to do, right? It's really time consuming, it's error prone, annoying. Also, I mean, you could appreciate it, but it's not even that some human likes to do this. I would argue in general, all the brain power of humankind is way better spent of doing high level stuff. And in whatever means, whether it's simple imperative code like this, or some higher level functional description of, hey, I want this set of memory moved in, like, if you describe it like this, or more high level, like whatever. The compiler knows all the microprocessor instructions and architecture alignment things, the penalties of misaligned code. I would argue of all the complexity, so basically the compiler has mostly the infrastructure to generate the most optimized code, and it should have, right? The compiler should optimize all the most complex C code templates, like all of the everything from kernel, from network byte processing, like to image processing, to sound processing, to the most complex codes that you would write, whether it's 3D, like a 3D engine, texture, like so much really complex code. The compiler should optimize the most perfect ideal way to your microprocessor at hand, right? And the biggest complication I would understand is for the compiler to actually know, like, this is some, like, not like some small internal fun function, like some small helper function, but like this is some high performance. As simple as it, we're talking about such simple stuff, right? String copy, mem copy and stuff. Such simple stuff, right? So basically the compiler, like I would even like that the compiler should expand this to this monster that is this mem copy stuff of aligning all the stuff, throwing all the AVX and stuff it has on it, and so on. You could, I mean, the compiler should know that this is being exported, so it's probably not some tiny little fun thing. It shouldn't do that with. It shouldn't optimize much. I would even, for me, it would be fine if there would be some attribute, whatever the attribute syntax is. Maybe even actually not. I switched to. Where is even? I think it's something like this. Maybe not there. Something I always forget. Also, maybe it should be there. If for me it would be fine if there would be some attribute like optimize the heck out of it, whatever. And there is another thing, so that the glibc has multiple variants, but so nothing is not solvable, right? So it is basically compiling this multiple times, because in glibc and muselibc, probably uselibc, and the Linux kernel, there are multiple variants, right? So basically what you want is also, but we have already attributes like that. So basically you would want some optimize here for march senver2 or stuff, or x86 I always forget what the like version 3, 4, whatever. So you would somehow, but that's not the compiler thing, right? That would be makefile like libc, Linux kernel and stuff, kbuild, kconfig, kbuild, because you would need this compiled multiple times. But this is like infrastructure, right? This is tooling. This doesn't matter for the compiler. It only matters, here's a string function, optimize the heck out of it with whatever march, like basically the Linux kernel would compile it with march, like dash version 1, version 2, version 3, ITVEC or whatever. But again, the tooling infrastructure. For the compiler, it has one compile unit. It gets this code, it gets it with this arguments, like optimize the heck out of it. I really mean this for this case, and don't optimize it away to some built-in, like basically disabled build and whatnot. And optimize this for this particular SIMD either set, because the C library and kernel, they have basically some kind of multiplexing of runtime CPU detection, because usually you want, even if you build all your program for x86-64 version 1 or 2, because you want to install your Linux operating system CD on all your hardware in the world, but you still want high-performance string functions for more than version 1 or version 2, basically version 3, version 4, SSE, AVX 512. But again, that is tooling, right? That is not, and yeah, just wanted to spread this world and also basically keep other people, also compiler engineers, thinking, because as long as the compiler cannot optimize this simple code, how should it optimize much more complex code? And yes, I'm very aware this is basically a pathological case, like you don't have memcopy in a 3D application except calling memcopy. I'm very aware that there are multiple surrounding optimization boundaries and so on. But again, I would argue it should be possible. It is ridiculous that 50 years later it is not necessarily, except LVM is doing it a little bit, not yet as high performance as glibc maybe. So yeah, it should be something more like even more simplified than that. They are on the right track here, but it is, I still find it ridiculous that we still have assembly optimized code for this simple. Sure, you need assembler code for loading page tables, for loading microprocessor instructions that either control registers like debug. Of course, there is no like loading, accessing debug registers except on RISC-V model specific register stuff that are a little bit more well defined than x86. But so of course for that you need x86. For that you need assembly code. You can't do that with C. But for this, I would argue, if a compiler, I mean, this should be the most, like basically, as I said some 10 minutes ago, this should be the most simple test case for your high-performance compiler. If it cannot optimize the heck out of it, you have not reached optimization, like you have not reached all the optimization possibilities of your compiler infrastructure. And you would probably also not, although it's a little bit different, as I said, I'm very well, it's a very, but I mean, hey, it's the most simple pathological case of that. All the 3D optimizations and image and sound and speech processing and neural networks and stuff are only more complex than this simple loop, right? Like if your compiler, in my opinion, I would argue if your compiler infrastructure cannot optimize the most optimal heck out of such a simple function, you will probably miss a lot of optimization possibilities for all the really complex 3D math matrix code to come. Anyway, just wanted to share this observation and my 2 cents. We will probably sometime soon write our own JIT code just because for our own super simple 10% complexity for 90% of the functionality or so project. And we'll be curious to see. Of course, I'm aware that this is a very complex topic. This is why it took 50 years. I just want to motivate more compiler engineers to take more of a look at it and see what optimization potential we are, which low-hanging fruits we leave there in optimization potential. I hope you enjoyed this and learned something with a little bit of background. What are the complexities here? We have some comments, so let's quickly check those. Try not to talk too long about this, because otherwise it always gets too long here. The problem is that language doesn't have the ability generally to articulate the details needed to truly optimize too many undefined situations. Well, I would argue this is the most simple form of string copy, right? I mean, what is there not? I mean, the compiler would, I mean, besides the compiler recognizes that, optimizes this to build in memcopy. But as I said, there is like, copy this from there, align it, use the widest word size, and like, yeah, I would argue, I mean, if it's not simple, if it's not possible for this simple code, there truly are bigger optimization lost potential in your compiler if it can't optimize it. Which is why some compilers end up just recognizing certain, well, I mean, I would hope they don't recognize who functions, right? They certainly recognize some patterns, unless it's some Microsoft spec cheating compiler from decades ago. Usually GCC and Clang do not necessarily have like match this function and hand optimized code like that. Certainly Microsoft Visual C++ had hacks like that, especially for the spec benchmark at times. But I mean, the compiler can, GCC and LVM can recognize string function patterns, right? And so they would map certain access patterns to build in memcopy. So they would do that, but yeah. Should be able to inline the most optimized version of the header. Anyway, that's it for this video. I hope you enjoyed this, learned something. Even if you're new to programming, I hope you understood a little bit why we write high-level code and how it maps to through various layers to assembly here. And even if you are a compiler guru, I hope you get inspiration to how to further improve it, even if it's, yes, I understand it's the most simple thing in the world. It just triggers me that we still spend human resources, like, not just saying, hey, AI, generate me the most optimal assembly code, but even without AI, assembler could, a compiler should, in my opinion, long story short, in my opinion, 50 years plus later, a compiler should be able to generate the most optimal code for such simple functions. Hope you enjoyed this and learned something. One more comment: compilers can't come up with tricks people use in assembly implementation, just not. You will be surprised how many tricks compilers recognize, so many patterns. But again, such tricks the compiler can use in other code as well, right? So like if you compile, that's what I meant with tricks of, I mean, it's all math and logic, right? I would rather argue the compiler should implement the logic necessary to recognize such patterns and also benefit in many other multimedia data processing cases. But yeah, leave in the comments below what compiler engineers are triggered by that. And again, I'm certainly aware that this is very complex, just that the compiler are already complex and can recognize and do so much stuff that I find it crazy. I mean, you could argue that the LVM people are aware of that and they basically move into the right direction. But yeah, leave in the comments below what you think, what's your take. Hope you enjoyed this, learned something. Don't forget to share, like, and subscribe. And I hope you have a good day or night and see you soon for the next fun stuff to come. Like our own JIT. It's a month anyway.